In this video, we'll discuss triangle foundations. Now, a triangle is a closed shape with three segments that are formed by three non-collinear points. The angle measures of a triangle will always sum to 180 degrees if it's in Euclidean geometry. So let's look at some examples of triangles versus not triangles. On the left, we have closed shapes made up of segments, and on the right, we have shapes that are made up of curves or are not closed, so they are not triangles here on this right-hand side. Now we can classify triangles by angles and by sides. In angles, we have acute, right, and obtuse angles as possibilities. Acute triangles have all angles less than 180 degrees. Here's an example of one. Now we can have a special case that's called the equiangular triangle where all three angles are 60 degrees, therefore they're all less than 90. That's a special acute case. We can also have right triangles where all three angles have to add up to 180 degrees. We have one 90-degree angle, which means the other two have to be complementary. And finally, you can have an obtuse triangle where one angle is greater than 90 and the other, on all three of them, will then add up to 180 degrees. We can also classify by sides, where one option is that it's scalene, so none of the sides are the same measure. And if none of the sides are the same measure, none of the angles will be the same measure as well. So that's a nice feature to recognize. If three segments are different, three angles will be different. And if the three angle measures are different, then the three segment measures will be different. We can also have isosceles triangles where at least two sides are congruent. So that's the key, at least two. Here we have two marked, but that means there's got to be a special case. And that special case is called the equilateral triangle, where all three sides are marked as congruent. So an equilateral triangle is isosceles. It's a special case of an isosceles triangle. Now, when we are trying to classify triangles, we're going to use both the angles and the sides to help us. And sometimes we have a special case that can occur because we had that equilateral equiangular triangle. If it's equilateral, it's automatically equiangular and vice versa. And we call that a regular triangle. So anytime you see that word regular in front of a shape, it has a special meaning in geometry that it is equilateral and equiangular. That's important to remember. So let's look at some examples. Here we see a triangle where two sides are marked as congruent and we have this 40-degree angle. The two tick marks tell us that this is an isosceles triangle. And since it's isosceles, we know that the opposite angles from those two tick mark sides have to be congruent to one another. And that's really helpful as we're trying to solve this problem. Because what we can say now is that 40 plus 2x, one angle and the other angle, which have to be congruent, they have to add up to 180 degrees. So we can solve that and determine that both of those angles are 70 degrees, which means that since all three angles are less than 90, that's an acute triangle and it's isosceles. Now here we have another unique situation where we only have two angle measures. Well, how's that enough? However, we recognize that the three angles have to add up to 180 degrees. And if I solve this, that'll become 130 degrees. Now you can say, well, what about the sides? We don't have anything there. But we know, as we said a minute ago, that if the three angle measures are different, then the three side measures will be different as well, which means this has to be scalene. Every side will have a different length than the other side. Finally, if you see a triangle like this where all three angles are marked as congruent, that makes it equiangular. As we said a minute ago, if you're equiangular, you're automatically equilateral. And when those two things are true, you are a regular triangle. Now, one of the properties we just used to help us do that classification was around isosceles triangles. And what we know is that if we have two sides marked as congruent, the opposite angles are going to be marked as congruent as well. And that can be flipped around to the converse. If the opposite angles are congruent, then the opposite sides are congruent. And so we can use those two properties to help us with isosceles triangles. Additionally, if a line bisects that vertex angle, that's only true if it's a perpendicular bisector of the base as well. And again, that's vice versa. If we know that it's a perpendicular bisector, then we know that line is going to bisect the vertex angle of the isosceles triangle. So let's use these properties to help us explore all the angles and measures that are in this triangle here. Now, nothing's told to us specifically other than what's marked on the image, and we can only take it for what it's worth. But the first thing we should notice here is that we have two marked congruent angles. So we know that this triangle has to be isosceles because of that, which means that AB and BC have to have the same measure because they're the sides opposite those two base angles. That also means that angle BCA has to be 37 degrees. The next thing I notice is that I have this perpendicular line segment here from BD. Because of that, it's going to make AC be bisected, and it's also going to bisect the angle ABC. So I have two different things being bisected, and now these measurements become easier to determine. Because I can look at just this left triangle and realize, oh, I've got a 90-degree angle, a 37-degree angle, and then I have my third missing angle. So I can add them together to make 180 degrees. And when I simplify that, I'm going to get that to 53 degrees. And because it's got double tick marks, because they're both the same measure, because it's bisected, I know both those angles are 53 degrees, which means the whole angle ABC would measure 106 degrees. Now I'm going to keep going. Now let's figure out AD and DC. So I know that by segment addition postulate, AD plus DC has to equal that entire length. But because it's a perpendicular bisector, I know they are the same measure. So I could just double up one side and say that that one has to be 8, which means the other one has to be 8 centimeters as well. Now I've got one last thing to figure out, which is how do I figure out that AB or that BC? Well, look what shape we have there. It's a right triangle. And one of the things we know about right triangles and their sides is we can use Pythagorean theorem to figure out segment AB's length. So I've got 8 squared plus 6 squared will equal that hypotenuse squared. And when I simplify that, I'll get a length of 10 centimeters, which means that AB and BC must both be 10 centimeters. Now our last thing we'll talk about with the foundations are the exterior angles of triangles. And in Euclidean geometry, they must always sum to 360 degrees. So here is an image to help us out here. If we look, 101 plus 147 plus 112, those three exterior angles all add up to 360 degrees. Now, the other relationship that's important to recognize is that the exterior angle is equal to the sum of the remote interior angle measures. So what does that mean? Well, here's an exterior angle. The remote interior are the two opposite interior angles from that exterior angle. So 68 plus 33 adds up to 101 degrees. If I look, 112 is equal to 79 plus 33 degrees, and 147 degrees is equal to 79 plus 68 degrees.